Hi everyone, welcome back to my channel. This is Professor Hare Krishna, and in today's session we shall start off learning about one of the important concepts of physical chemistry, that is phase equilibrium. Before going to the main concepts of the topic phase equilibrium, we shall give a bit of interest, bit of focus towards the word equilibrium. We need to understand what is the exact meaning of the term equilibrium. We know that in the field of chemistry, the main interest is given towards understanding the terms reactions as well as the reactivity of the reactions. And the reactions may be allowed to take place either in an isolated system or in closed system as well as in open system. But if you consider the reactions that are allowed to take place in a closed system, most of the chemical reactions that are taking place in a closed vessel, they do not go to completions. And under these conditions, when a reaction is allowed to take place in a closed system, the reaction, once it is started, it will continue for some time at a diminishing rates. That means the reaction proceeds with decrease in the rate of reaction, because the rate of reaction is dependent on the concentration of the reactants. As the concentration of reactant decreases, obviously the rate of the reaction also decreases. And as we said, when the reaction is allowed to take place in a closed system, the rate of the reaction will get decreases. And if you notice the course of the reaction will proceed up to a certain stage, and at one stage the reaction is appeared to be stopped. But if you do a careful observation, even though the reaction is appeared to stop, the reactants are still present at that condition, but they do not appear to change into products anymore. One question comes to our mind: what happened to the reaction? Still the reactants are there, but there is no observation of conversion of reactants into products. What is the thing that is happening in that particular stage? The answer for that particular question is, at one particular stage, which is for the reaction which is taking place in a closed system, the products starts to react themselves and they convert back into reactants. How the reactants are converting into products? At one particular stage, the products self reacts with each other and they converts into reactants, means the backward reaction have been initiated. So for both forward and backward reactions will start to take place in a closed system. And at one particular stage, the rate of forward reaction and rate of backward reaction will becomes exactly equals to each other. That means in what speed the reactants are converting into product, in the same speed the products are converting into reactant. Because of this reason, even though the concentration of reactants are still present, they are not observing to change into products because of a same rate for both forward and backward reactions. And if you observe, at that particular stage where the rate of forward and backward reactions are same, the concentrations of reactants are exactly equals to the concentration of products because of the same rate for both forward and backward reaction. And the reaction at this condition where the rate of forward and backward reactions are same and the concentration of reactants and products are same, at that particular stage, at that particular condition, we used to say the reaction is attained the state of equilibrium. And the attainment of equilibrium by a reaction can be easily recognized by noticing the constancy of observable properties. The constancy of observable properties. That means the properties that are used to specify a reaction which is taking place in a particular type of system. So the observable properties will become constant at the state of equilibrium. And which are those observable properties? It may be pressure, temperature, concentration of the reactant or product, it may be density, or even it may be color. There will be no changes in either of these properties, whichever may be suitable in a given case. So just by noticing the constancy in these observable properties, we can easily say that the reaction have attained the state of equilibrium. And with respect to a particular type of reaction, the equilibrium is of two types. The first one is called as homogeneous equilibrium and the second one is called as heterogeneous equilibrium. So the names itself telling you about the meaning of these two terms, that is homogeneous equilibrium and heterogeneous equilibrium. So I shall give a brief discussion regarding both the types of equilibrium, that is homogeneous and heterogeneous equilibrium. Firstly, we shall consider about homogeneous equilibrium. The name itself telling you homo in the sense same, geneous in the sense phase. So the equilibrium in which the constituents of the reactions are existing in the same phase, that is in the same physical state, that is both reactants as well as the products of the reactions that are present at the state of equilibrium. Both reactants and products will be existing in same physical state, that is in same phase. Such a kind of equilibrium in which both reactants and products are present in the same phase will be called as homogeneous equilibrium. So let me say once again, homogeneous equilibrium is the equilibrium in which both reactants and products will be existing in the same phase. So we can consider a simple gaseous reactions as best examples for the type of homogeneous equilibrium. So we shall consider some simple examples so as to illustrate the homogeneous equilibrium. So firstly, we shall consider N2, which is a gaseous material which undergo oxidation by combination with the oxygen gas reversibly. So the equilibrium will be shown by with this symbol. So N2 gas will combine with oxygen gas so as to form NO, nitric oxide, which is once again a gaseous material. So both reactants and products are present in same physical state. So this comes under homogeneous equilibrium. Once again, you can consider one more example. Hydrogen gas will be combining with iodine vapors so as to form the product of 2HI, once again in gaseous form. So here both reactants and products are present in the same physical state, that is all are gaseous materials. And we can give one more example, say COCl2 phosgene, which is a gaseous material, so which will reversibly changes or will be in the equilibrium with the carbon monoxide, which is once again a gaseous material, and Cl2, once again a gaseous material. Or else you can go with the decomposition of phosphorus pentachloride. When gaseous phosphorus pentachloride is subjected to the process of decomposition, it changes into PCl3 and chlorine gas. Both are gaseous forms. So here you can notice I have given 4 reactions, but these 2 reactions belongs to one type of homogeneous equilibrium and these 2 belongs to other type. So in what way? You can notice here there is 1 mole of nitrogen and 1 mole of oxygen. Both are combining to give 2 moles of nitric oxide. So the number of reactant molecules are exactly equals to number of product molecules. And here also the same, 1 plus 1 totally gives 2. But here you can notice 1 mole of phosgene, that is carbonyl chloride, splits to give 1 mole of carbon monoxide and 1 mole of chlorine. So that number of reactant molecules and number of product molecules are not equals to each other. So these are the 2 types, that is the number of reactant molecules are equals to number of product molecules in this case. And if you come to this one, the number of reactant molecules are not equals to number of product molecules, but still both the types of the reactions comes under homogeneous equilibrium since both reactants and products are present in same physical state. The second type of equilibrium is heterogeneous equilibrium. The name itself telling you hetero in the sense different and geneous in the sense phase, that's nothing but physical state. So a heterogeneous equilibrium is one in which at the state of equilibrium the reactants and products will be in the state of different phases. Such a kind of equilibrium will be called as heterogeneous equilibrium. That means the constituents of the equilibrium should exist in more than one phase in case of heterogeneous equilibrium. So we shall consider one or two simple examples so as to illustrate the heterogeneous equilibrium. So if you consider the limestone, that is calcium carbonate, which is a solid material, when it is subjected to the process of decomposition at the state of equilibrium, calcium carbonate will splits to give quicklime, that is calcium oxide, which is once again a solid material, and that results in the liberation of carbon dioxide, which is a gaseous material. You can notice here calcium carbonate is solid, quicklime is once again a solid, but carbon dioxide is a gaseous material. So reactants and products are present in more than one physical state. So this comes under heterogeneous equilibrium. And one more example we can give, the very simplest salt, that is ammonium chloride, which is a solid material. When it is allowed to undergo decomposition, it gives NH3, which is a gaseous material, and HCl, once again a gaseous form. So here also you can notice the solid material is in equilibrium with its products, which are in gaseous form. So the reactants and products are present in more than one physical state. So this also comes under heterogeneous equilibrium. So here we have given the explanation regarding the types of equilibrium based on the physical states, in a strictly speaking way, based on the phase of the constituents that are present at the state of equilibrium of a reaction. So among these two, this one, the heterogeneous equilibrium, is very important. And while analyzing the concepts of heterogeneous equilibrium in the year of 1876, a scientist by name J.W. Gibbs. He is a person, a very brilliant person. In the year of 1876, while analyzing the heterogeneous equilibrium, while investigating the heterogeneous equilibrium, he observed many important factors, and in order to explain all those things, Gibbs proposed one important concept that is called phase rule. This is the most important parameter we are supposed to learn to understand the whole and soul concepts that comes under phase equilibrium. This phase rule is a very important tool, and it is used for the quantitative treatment of a system that is existing in the state of equilibrium. As well, the phase rule is very much useful in order to predict the conditions that are supposed to be specified for a system in order to exhibit the state of equilibrium. That means, in order to define a system which is existing in the state of equilibrium, which are the conditions we are supposed to be considered so as to specify in order to define the system which is existing in the state of equilibrium. For that, the phase rule will give a lot of information. And according to Gibbs, the phase rule is simply given by F is equals to C minus P plus 2. This is the phase rule enunciated or proposed by Gibbs in order to explain the concepts of heterogeneous equilibrium. Here F in the sense it is number of degrees of freedom, C is the number of components present in a system at equilibrium, and P is the number of phases that are phases of the constituents of the equilibrium, and 2 is a simple constant. So once again, F is number of degrees of freedom, C is the number of components, P is the number of phases. So in order to understand the whole and soul concepts of the phase equilibrium, first we need to know the exact meaning of all these three terms, that is phase, components and degrees of freedom. And now we shall see what are the exact meanings of phase, component and degrees of freedom, and how to calculate these three things for a particular system. The first term that comes in phase rule is P, that is phase. A phase is actually, if you consider a system which is present at the state of equilibrium, we will be having so many constituents. And if you give a careful observation, careful focus on all the constituents that are present at the state of equilibrium, and if you consider each and every constituent as one part of the system, the homogeneous as well the physically distinct part of the system. Physically distinct part of the system which is bounded by a surface, and if that part of that is the homogeneous and physically distinct part of the system, if that is possible to separate from other parts of the system, separate from other parts of the system, in particularly through a mechanical method. Mechanically, that means a phase is a homogeneous, physically distinct part of the system which is separated by a boundary or a surface, and if that individual part of the system, if it is able to separate from other parts of the system through mechanical method, then that each physically distinct part, individual physically distinct part of the system will be called as phase. So we need to focus, the material should be, the parts should be homogeneous, and they are supposed to be, we should able to notify the individual existence of that part from the other parts. That should be homogeneous. If you are having one complete system and if everything is appearing as homogeneous, then that will be one phase. If you are having two materials, if they are completely mixing with each other so as to appear as a single system, then that is also a one phase. But when you are having two constituents and if they are not mixing with each other, that means if they are not homogeneous, if the system is not homogeneous, then we can easily notice the distinct occupations of those two components. Then we can say they are two phases. So we shall consider some examples so as to illustrate the phases in a system. So if you consider the mixture of gases, if you consider the mixture of gases, so for example, the mixture is consisting of H2, N2, O2, like this. So if you're having a mixture of gases, these gases are completely they are completely mixed with each other. They do not, it is not possible to identify here the oxygen molecule is, here the nitrogen molecule is, and here the oxygen molecule is, hydrogen molecule is, like that. It is not possible to differentiate the molecules when they are present in the mixture. All the components which are present in a mixture is appear to be the one system only, one component only. That means all these three are mixed together to form a homogeneous content. So that in this case we used to say, even though we are having three constituents, they are all gaseous materials, and we used to say the number of phases in this particular mixture is equals to 1. But if you consider the mixture formed by alcohol and water. So alcohol is completely miscible in water so as to form a homogeneous solution. So there you cannot notice here the alcohol molecule is and here the water molecule is. So this also form a single homogeneous system though two constituents are present. So for this case also the number of phases are equals to 1. But if you go with the mixture consisting of carbon tetrachloride and water, we know that carbon tetrachloride is an organic liquid and water. They are here, carbon tetrachloride is non-polar and water is polar, so they are not miscible to each other, though both are present in the liquid state only, but they form an individual parts in a system. So they are not going to mix with each other. They present physically distinct parts. They are present at distinct parts of the system. So though they are existing in the same physical state, they are completely not miscible with each other. They are not forming the homogeneous system. Therefore, this will be a separate phase and this will be a separate phase, so that the number of phases in a system consisting of CCl4 and H2O will be equals to 2. And if you go with one simple reaction pathway, say let us consider the decomposition of calcium carbonate. So calcium carbonate, which is a solid material, upon decomposition at the state of equilibrium, it will be having calcium oxide, which is in the solid form, and carbon dioxide in the gaseous form. So here calcium carbonate is a distinct part and calcium oxide is a distinct part. Carbon dioxide is a distinct part. So here we are having totally 2 solid phases and 1 gaseous phase. So totally it is a 3-phase system. So like that, by physical observation, if it is homogeneous or heterogeneous, by observing that whether they are forming a single constituent or whether they are formed by more than one constituent, and whether they are forming homogeneous system or heterogeneous system, by noticing the physically distinct existence of the components in a system, it is possible to judge how many phases are there in a particular system which is existing at equilibrium. So that we can easily notice the number of phases in a system. Say for example, the second factor that comes in phase rule is component, simply indicated with the term C. So if you consider one particular reaction which is present at the equilibrium, in that particular reaction, the number of independently variable constituents by means of which the composition of each phase can be expressed either directly or in terms of chemical equations. That means if you consider the constituents of all the constituents of the system, if one constituent is completely different from its chemical composition from the other, so for example, let us say we are having 2 constituents at the state of equilibrium. If both are having the same chemical composition, then though 2 constituents are present, the number of component will be 1 because both are having same chemical composition. Let us say if we are having 3 constituents at the state of equilibrium, if the chemical composition of the first 2 constituents are same and the third constituent is different, then we used to say it is a 2-component system. If we are having 3 constituents at the state of equilibrium, if the chemical composition of all the 3 constituents are completely different from each other, then we used to say the number of components equals to 3. That means the components are supposed to be noticed just based on the composition. That means the number of independently variable constituents by means of which the composition of each phase can be expressed distinctly. So the number of components can be said as the number of independent compositions. Number of independent compositions that are present in a system will be taken equals to number of components. So we shall do the illustration. So for example, we shall consider the equilibrium that is existing between ice and liquid or water. Okay, so the composition of ice is H2O and the chemical composition of water is once again H2O. But here ice is in the solid phase and water will be in the liquid phase. Though there are 2 phases, the chemical composition of both the constituents is same, that is H2O. Therefore, the number of components in this particular system will be equals to 1, and we used to say that as 1 component system. Okay, and if you consider the system of sulfur, so sulfur exists in 4 phases. Say for example, sulfur will be existing in rhombic phase, sulfur will be existing in monoclinic form, and sulfur will be in the form of liquid as well. There is a vapor sulfur. So there are four phases: rhombic, monoclinic, liquid, and vapor sulfur, means the gaseous state. So though there are four phases, the chemical composition of all these four forms remains the same. Therefore, this system is also consisting of number of components equals to 1. And if you go with the other system, say for example, once again let me consider the same mixture CCl4 and H2O. And here there are two phases, CCl4 and H2O. They are completely distinct parts, and CCl4 is completely different in its composition compared to water. So the system consisting of CCl4 and H2O having two distinct chemical composition, so the number of components for this system will be equals to 2. So we need to observe the distinct chemical compositions of the constituents that are present at the state of equilibrium, so as to say the number of components present in a particular equilibrium reaction. So in case of a chemically reactive system, we can observe the presence of more number of constituents. More than one component will be present in a chemically reactive system, and in order to calculate the number of components that can be present in a chemically reactive system, we can use a simple mathematical formula such as C, the number of components, is equals to N minus E. Here C is the number of components, and E, as I said, in case of chemically reactive system. So reactive in the sense we will be having a chemical reactions. So here, in order to decide or predict or to calculate the number of components present in a system, in a chemically reactive system, first we should notice the number of independent equations that are taking place in a system at the state of equilibrium, which is having n number of constituents. So E is the number of independent equations that are taking place, that are possible with n number of reactive species. So by knowing the number of species that are present at the state of equilibrium in a system, as well as the number of independent equations that are developed by these n number of species, it is possible to calculate the number of components that are present in a system. And for this we shall do some simple illustrations, and we shall calculate the number of components in those systems. If you consider the system consisting of KCl, NaCl and H2O, where KCl and NaCl were dissolved in water, so we'll be having a single phase, because KCl and NaCl and H2O completely mix up with each other so as to give a single phase. That means these three will mix with each other to form a homogeneous system. So the number of phases will be equals to 1. But our intention is to find out the number of components in this particular system. So in order to find out the number of components, we have to go with the equation, that is C is equals to N minus E. So first we should go with the number of independent equations that these components can frame up. So KCl can react with NaCl. So when these two were reacted, we are going to get the same thing, KCl and NaCl, because here also we are having Cl as anionic part. When they are exchanged also, we are going to get the same thing. So there is no change in the products as well as reactants. In that case, the number of equations will be taken equals to 0, because we should get different products when reactants were reacted with each other, so that the value of E, the number of independent equations, will be taken equals to 0. And N is number of components. We are having KCl, we are having NaCl and H2O. So totally we are having N, that is N is equals to 3 constituents. So we can calculate the number of components by using the formula C is equals to N minus E, provided the value of N is 3 and there is no independent equation that is taking place. So 3 minus 0. So the system consisting of 3 components. But if you consider the other system, say KCl and NaBr H2O. If you consider this system, so we can notice the existence of the reaction. So for example, KCl can react with NaBr. Now the displacement reaction is possible between KCl and NaCl. So you will get KBr plus NaCl. So there occurs displacement reactions between KCl and NaBr. So here we have one independent equations and no other reaction is possible apart from this. So the number of independent equations are 1. So if you go with the N, that is the number of components. So KCl, NaBr, KBr, NaCl and H2O. So totally we are having 5 number of constituents. So therefore C is equals to N minus E, that's equals to 5, right? 1, 2, 3, 4, 5. 5 minus 1, so there will be 4 number of constituents in a system. So there are 4 components in the system. So shall take one more example with more number of constituents and more number of independent equation. So let us consider the system consisting of NaCl, KBr, KCl, NaBr, as well the ionic forms, that is K plus, Na plus, Cl minus, Br minus and H2O. So these are the constituents that are present in the system. So for this we should frame the independent equation. So first we shall consider NaCl, which can combine with KBr so as to form a displacement reaction that can exist at the state of equilibrium. So upon displacement you will be getting NaBr plus KCl, and after this, so no combination or displacement reactions. Still we have the ionic form, so we should go with the dissociation reactions. NaCl will splits to give Na plus and Cl minus. KBr will undergo dissociation so as to give K plus and Br minus, and NaBr will undergo dissociation to give Na plus and Br minus, as well KCl will undergo dissociation so as to give K plus and Cl minus. So totally we are having 1, 2, 3, 4, 5. So the value of E is equals to 5. So there are 5 independent equations that are taking place. And if you go with the number of constituents, so NaCl, KBr, KCl, NaBr, K plus, Na plus, Cl minus, Br minus and H2O. So totally 2 plus 2, 4, 4 plus 2, 6, plus 2, 8, plus 1, 9. So there are 9 constituents that are present at the state of equilibrium. So the value of number of components C is equals to N minus E, that is 9 minus 5, that's equals to 4. So the number of components in this particular system are equals to 4. So if you go with the last example, let us consider the dissociation or decomposition of the limestone, that is calcium carbonate. So will be in equilibrium with CaO and CO2. So the number of constituents are CaCO3, CaO and CO2. So there is only one possible equation, that is E is equals to 1, and the number of constituents are 1, 2 and 3. So the number of components will be equals to N minus E, that is 3 minus 1, that's equals to 2. So it is a 2-component system. You may get a question. So CaCO3, CaO, CO2, we are having 3 constituents. But how we are getting only 2 components? Because carbon dioxide can escape from the system. So by leaving this, we will be having only these 2, that is calcium carbonate and CaO. Only these 2 will be absorbed with a distinct chemical composition. So we will be telling this is a 2-component system. And that's about the way of calculation of number of components in a system. The last parameter which is present in the phase rule, that is F is equals to C minus P plus 2 is F, that is number of degrees of freedom. So in the beginning of the video we said that The attainment of equilibrium by a reaction can be noticed by constancy in the parameters such as pressure, temperature, concentration, density, color of the reaction, color of the reactants, whichever may be suitable at a particular case. In order to define a system which is present at the state of equilibrium, for that purpose we have to specify certain independent variables such as temperature, pressure and concentrations, or even it may be composition of the constituents. So among these things, either 1 or 2 or 3 or all the 4 parameters are supposed to be specified in order to define the state of a system at the condition of equilibrium. So how many independent variables are supposed to be required and which are supposed to be specified to define the system at the equilibrium condition? That number of parameters required will be called as degrees of freedom. That means the number of independent variables. The number of independent variables supposed to be specified to define the system. To define the system at which condition? At the state of equilibrium. Those number of independent variables are supposed to be specified in order to define the system at the state of equilibrium. The number of independent variables we are specifying are called as degrees of freedom. So for example, if you consider the state of a pure gas. So if you consider the pure gas, in order to define the state of or the system consisting of pure gas, we are supposed to use either pressure and temperature or temperature or pressure and volume. We have to use either pressure and temperature and pressure and volume. But in actual sense, the volume of the system can be easily calculated from the equation of state. So the degrees of freedom for a system consisting of pure gas are only 2. That means we need either pressure and temperature. We need only pressure and temperature, no need of volume. So only pressure and temperature are required in order to define the system consisting of pure gas. Volume is not required. But if you consider one more example, say the equilibrium which is existing between the liquid form of the water and its vapor state. So when you heat, means when you increase the temperature, the liquid form will goes to its vapor state. When you cool the temperature or when you cool the vapor, temperature will be brought down and the vapor will get changed into liquid. So temperature is one of the factor which is supposed to be specified in order to define this particular equilibrium. But you can notice when you increase the temperature, pressure will also increase. And when you lower the temperature, obviously the pressure value will also get changed. That means the equilibrium pressure of water is having a fixed value. So if you define the temperature, pressure will be automatically known. And if you know the pressure value, temperature value will be automatically known. So that in order to define this particular system, either we can use only pressure or we can use only temperature. No need to define both the system, both the parameters, either temperature or pressure. If you define the pressure, automatically temperature will be known because pressure and temperature are directly proportional. And if temperature is used for defining this system, pressure will be automatically known because they are directly proportional to each other. So either pressure or temperature, any one parameter is enough to define this system at equilibrium. So for this system, the value of F is equals to 1. And here in this case of pure gas, we need both pressure and temperature. Therefore, the value of F will be 2. Like this, the system may have either one parameter required for defining of it or 2 parameter, 3 parameter, or even in some cases no parameter is required to define the system also. So for that we shall consider one simple example. Let us consider the equilibrium which is present between ice, water which is existing in the liquid form, and its vapor state. So here you can notice we are having 3 phases, ice, water and vapor, where at the state of equilibrium all these 3 properties are coexisting. So when they are coexisting, it is not required to specify any parameter so as to define that system. In such case, the value of f will be equals to 0. So depending upon the number of parameters we are using for defining the state of equilibrium for a system, we used to say as if f is equals to 0, the system is said to be invariant. That means no parameter or no independent variable is required or supposed to be specified to define the system. And if f is equals to 1, the system is said to be monovariant or univariant. And if the value of f is equals to 2, then the system is said to be bivariant. That means in order to define a system, there is a requirement of 2 independent variables. Okay, and by knowing one parameter, the other parameters can be easily notified. So for example, with the higher value of components, the number of degrees of freedom also higher. So greater the value of number of components, greater will be the number of degrees of freedom for a given number of phases. Means phases are supposed to be fixed. So in that case, with increase in the number of components, number of degrees of freedom also increases. And for a given value of component, with increase in the value of number of phases, the number of degrees of freedom will get decreases. So these two are inversely proportional for a given value of C, that is the number of components. Okay, and for a given number of components, the number of phases will be maximum when the number of degrees of freedom are equals to 0. You can notice over here, when the number of degrees of freedom are 0, here you can notice all the 3 phases are present, both solid, liquid as well as gaseous form. So actually we have the phase rule, that is f is equals to c minus p plus 2. So we can, observing the system, we can easily judge the number of phases in a system, and by using the formulae or by observing the number of distinct chemical compositions, it is possible to count the number of components in a system. And by knowing the value of number of components and number of phases, it is possible to calculate the number of degrees of freedom so as to say whether the system is invariant, univariant, bivariant or trivariant. So and this is about the parameters that comes in the phase rule, that is f is equals to c minus p plus 2. And that's about the basics. In the next video, we shall go with the complete derivation of the phase rule that was given by the Gibbs. If the video is useful for you, please like it, share it, and please do subscribe to my channel and press the bell icon so that you will get the notification for any new update in my channel. Thank you.